Everybody tell me what color this is? It's yellowish, right? Alright, we're gonna use it to predict your future. Do I have any volunteers? Since you're at the front, what's your name? Lizma? Uzma. Round of applause for Uzma. Come up front. And round of applause for Jakai. First, you guys gotta get some gloves on.
Safety first. So do you guys know what reading tea leaves are? Maybe from Harry Potter, that you look at the bottom of the teacup and determine what your future is. So we're gonna do something kind of like that, but with the colors of these solutions. So we're gonna read your chemistry future.
All right, guys, so we're gonna shake this now. All right, we want everybody's encouragement, so we're gonna be singing together. All right, we're gonna be singing, shake it, shake it, shake. All right, so let's practice right now. One run. Shake it, shake it, shake. Again. That's it. Louder, come on.
All right, let it rip. Start shaking.
All right, start.
Shake, shake, shake. Shake, shake, shake. Shake, shake, shake. Shake, shake, shake. All right, let's see. Ooh, look at that. That is not red anymore, huh? And that
This
sure
is
isn't
not yellow anymore.
Ooh, we're getting teal over here where we used to see yellow, and we've got greenish, brownish, wine. So, who wants to read her tea leaves? What does teal mean? What does her future hold?
She should take chemistry. If it oscillates from red to black, you should go into accounting. Okay, if it turns green, go into biology. If it turns blue, take up chemistry.
Yeah. What about this one?
I'd stay away from that guy.
I think he's
Look
a
at what just
chemist.
happened. Scene 4 was blue, now it went back. All right.
Uh-oh, you better not take up chemistry.
That one's gonna go back really soon. I think you gave it a little hard shake. Shake it so hard, it doesn't want to go back anymore.
It'll turn. Slowly, but surely. Well, get in there.
All right, that's the color bottle for you.
Yes. All right.
Oh, turn it.
Alright, you guys. So earlier on, we were making some drinks for our party, but milk, water, and juice are pretty boring. Since Mimi was our birthday girl, we let her decide what drink she wants.
Yeah, I'm not a milk person. Would you like maybe Coke instead?
Coke sounds like a party drink. So let's make some new drinks.
Okay, 2 waters for you, 2 Cokes for me.
So we've got a bit of a party theme going on here. Who likes glow sticks? Glow sticks, right? That's what really makes a party. So I've got 2 parts of the glow stick. You know when you crack a glow stick and you hear that crack? What's cracking is a little piece of plastic that has this inside, and the rest of the glow stick has this inside. So we're gonna make our own glow stick. Or glow flask, what have you. That's pretty.
Does anybody know what that's called? That glowing thing? What it's called chemiluminescence. Okay, it also is sometimes called bioluminescence. Can you think of an example in nature that does that? What? I'm sorry. I'll give it to you. That was a hell of a one. I was just thinking of a firefly. How many of you have gone to the beach in the evening? Have you ever watched the waves turn over when they crash? What color do they look like? They look like very bright white. That's actually, I'm not sure what it is, but a small mammal or animal in the water that actually bioluminesces. And the reaction that Victoria just did is the same reaction that gives rise to the glow in the firefly. It's called chemiluminescence. The chemical reaction produces enough energy that the molecules emit light.
Ladies and gentlemen, you like the color changes, I see. Yes. Okay, well I got another one for you. This one's called Fireworks Colors. I go from the dynamite soap to fireworks. So have you ever watched a fireworks show? Yeah. All right, so who doesn't like a good fireworks show? And if you, don't answer that. And if you've watched a good fireworks show, you should have fireworks of different colors. Well, what produces the different colors is basically chemistry. Each of these that I'm pouring into each of these Petri dishes is a different metallic salt. And each metallic salt produces a different color when heat is applied. Have you guys learned about something called the excited state? Yeah. Okay. So in fireworks, burning gunpowder produces the heat required for atoms to achieve the excited state. Here I'm using a flammable liquid. So basically the same idea. And the metals in the metallic salts are going to absorb that heat energy, and this basically excites the electrons, which means they jump up to higher energy levels. Now they don't stay there too long. They stay there about as long as I stay in the air, probably shorter. They will return back down to low energy levels. But when they do that, they release the energy that they previously absorbed in the form of light. But not just any light. Light of specific wavelengths. And you see it as different colors. Now this will take about 30 seconds to really develop, maybe a minute. And basically I just set the desk on fire. I set the desk on fire! How are you supposed to respond? Okay. And if you look carefully, these flames are developing different colors. These are the colors that are responsible for the different colored fireworks. And since we all live in the New York metropolitan area, where we see a lot of traffic, you're probably used to seeing cars broken down on the side of the road. And if a police man comes, a police officer will usually put a roadside flare behind the car to warn people approaching that there's an emergency up ahead, to slow down and go around. Those roadside flares are basically little cylinders that burn red. That kind of red. The red that's developing right now. And once it's all burned up, it goes out. But that's what's producing the red color. So ladies and gentlemen, fireworks colors.
Did you say fireworks?
I said fireworks.
I like fireworks.
You like fireworks?
I do. What do you think? What do you think? Can we make a firework here? Yeah! Let's make one. So we're going to use some of this liquid he uses to light it on fire, and we're going to make a propellant out of it. So we're going to take this little thing here. See it? It never works for me, Henry. I don't know why you say it works. It never works for me. He does it. It works every time. But what's supposed to happen is this is supposed to show that we can send this bottle to the top of the roof here. What do you guys say? Yeah. All right, so let's see what it really does work. Take my bottle here. Now you guys have to pay attention to the color, because you had a quiz, a lesson over there. What color this is supposed to be? 3, 2, 1. Ready? 3, 2, 1. Ready? Count down. 3, 2, 1. Fireworks right here in the building. What color was it? What color was it? Autumn. Autumn. I like autumn. Red.
Hey, is that just any red? What kind of red is this?
That's like lithium red. They call that magenta.
and bases. You know what an acid and a base is? Yes. Okay, I have in this tube here water and a base called sodium hydroxide. How can I tell that I have sodium hydroxide in here and not just water? What can I do? I can measure the pH, right? I can get a pH meter if I want, litmus paper, but I want something a little bit more exciting. So what I'm gonna do, I'm gonna add, it's called a universal indicator. That's going to change color based on the pH. I said ammonium hydroxide is what? A base. So we can see that the color is, what's the color? Blue. See, it's a nice little blue here. Okay, what do you think would happen if I added an acid to it? Think it's going to turn red? This is a universal indicator, so it will turn red, but I need an acid. You guys have seen this before, right? What is this? This is dry ice. Is this an acid? You sure?